Hi, my name is Hazim bin Muhammad Razali. My matrix number is CE230046. So, digital signal processing is widely used to analyze and extract useful information from digital signal. In real world systems like audio communication, ECG monitoring, and industrial sensing, often affected by noise that must be filtered for reliable data. One effective method is frequency domain filtering, where signals are transformed using discrete Fourier transform (DFT) or its faster version, the fast Fourier transform (FFT). While DFT is accurate, it's not efficient for real-time use. The FFT solves this by reducing processing time, making it suitable for platforms like MATLAB and Arduino that we are using in this project. This project demonstrates practical DSP comparing manual data, MATLAB and Arduino-based FFT implementation to validate their consistency and show how frequency domain filtering can improve signal quality in both simulation and embedded systems. Previous studies have widely used the discrete Fourier transform (DFT) and also FFT to analyze and filter the noisy signal in the frequency domain. MATLAB is commonly used for its built-in FFT function, while microcontrollers like Arduino allow real-time FFT implementation for embedded application. However, most work focus on either software or hardware platforms separately. This project addresses that gap by comparing manual MATLAB and Arduino-based FFT methods, showing how frequency domain filtering can be effectively applied across different environments.
Hello, my name is Iswan Irzan. So for my part, I will explain the problem background of this project and also the objective of this project. So digital signal processing or DSP is widely used in systems like audio, biomedical, and industrial automation. One major challenge is noise, which affects signal accuracy. To reduce noise, we use frequency domain filtering by converting signals using the discrete Fourier transform or DFT, but since DFT is slow, we use its faster version, which is fast Fourier transform FFT. FFT makes real-time processing possible even on embedded systems like Arduino or Raspberry Pi. This presentation will show how FFT-based filtering improves signal quality in practical DSP application. So now let's move on into the project objective. So based on our finding, we have discovered five main objectives of this project. The first one is analyze noise effect on digital signals in real world use, compare time versus frequency domain processing methods, apply FFT for efficient noise reduction, build real-time DSP on embedded system, and the last one is assess FFT filtering accuracy and performance.
Good morning. Hi, my name is Muhammad Lakwana Hakim Ramli, market matrix ECE 230031. Okay, for our DSP project on frequency domain noise filtering, my part focus on Arduino implementation of the discrete Fourier transform or DFT. Okay, the input signal I'm working with is simple as n equal to 1 to 10, and the goal is to convert it from the time domain to the frequency domain using DFT. The DFT formula is xk total of Sn multiplied by exponent power of minus j to pi and k slash n. Okay, on Arduino, we can't handle complex number directly. I separate the equation into cosine for the real parts and the sine for the imaginary part. I implemented the DFT using two nest for loops, calculating the angle and accumulating the real and imaginary part separately. After uploading the code and checking the serial monitor, the output matched my team member manual DFT results, which is x0 is equal to 4, x1 equal to negative 1, x2 equal to 0, and x3 equal to negative 1. This proves that the DFT is correctly implemented and it's set the foundation for the further step like filtering noise by modifying frequency components.
Assalamualaikum and greetings everyone. My name is Muhammad Yosahi and my message number is CE3050. So I'm gonna explain on how we did the method simulation and the filtering. So my part on the project is focused on simulating the signal in MATLAB using FFT to analyze and filter out noise in the frequency domain. This is an important step because FFT allows us to see which frequency components exist in a digital signal, including noise, in real-world applications like ECG signal processing, vibration monitoring, or audio cleaning. This is how we detect and remove unwanted frequencies. In our project, we use the algorithm that is xn equals to 1, 2, 1, and 0 as an example, as a sample input. This signal has both low and high frequency content. Our goal is to identify high frequency noise and remove it using a simple low-pass filter in the frequency domain. So that's all for the introduction of the simulation. Thank you. Next, we're going to continue with the MATLAB simulation code. So in this section, I'll explain how we use MATLAB to analyze and filter digital signal using the FFT algorithm that we already working with. That is xn equals to 1, 2, and 1, 0. So next, we need to define a signal. At line 4, we define our input signal in discrete time. Then in line 5, we store the number of samples in a variable called n, which is used for plotting and indexing for later output. So next one, we perform the FFT. In line 8, we use MATLAB in FFT function to compute the fast Fourier transform. This is convert our time domain signal into the frequency domain, producing a complex output. After that, we need to display FFT and the magnitude. So in line 11, in line 12, we display the complex frequency components xk. Then in line 15, we calculate and display the magnitude of each frequency being using ABSX. And after that, we plot the magnitude spectrum. So in line 19 to 22, we generate a stem plot of FFT magnitudes. This helps us to visualize how much energy each frequency contains. The largest spike will appear at x0, the DC component, and smaller ones at higher frequency. After that, we apply frequency domain filtering. In line 26, we copy the FFT results into a new variable for filtering. In line 37, we simulate a basic low-pass filter by setting the higher frequency bins x1 and x2 to 0. This removes high-frequency noise. And next, we do the FFT inverse reconstruction. So in line 30, we use the inverse FFT to convert the filtered signal back to the time domain. This gives us a new, cleaner version of original signal. Then, lastly, we need to plot the original and the filter signal so we can make comparison. So in line 36, we plot the original signal. Then in line 43, we plot the filter signal after inverse FFT. The bottom plot should look smoother. This proves that our frequency domain filtering successfully removed the noise. So that's all for the simulation code. Okay, next I'm going to discuss the result for the MATLAB simulation code that we got here. So for the FFT output in the complex values, columns 1 through 2, we got the values of 4 plus 0j, 0 minus 2j, and columns 3 through 4, that is 0 plus 0j and 0 plus 2j. So in the method spectrum xk, we got the value of 4202. So next for the graph comparison, here we can see that we can compare original signal and the filter signal in the time domain. So for the top plot of, or we can say is original signal, is the top plot shows the original signal xn1210. As you can see, it has a sharp peak n1, n equals to 1, then drops quickly to 0, This kind of sudden change often introduce of high frequency components. Next, in the bottom plot, what we can say is a filter signal plot. In the bottom plot, you can see the filter version of the signal after we remove the high frequencies using FFT and IFFT. The values have changed roughly to 1.5, 1, 1.5, and 0. This shape is smoother with the sharp transitions removed, meaning we effectively reduce the noise in the signal. So, in the conclusion, this proof the frequency domain filtering works as we identified the noise components, in effectively remove them and reconstruct a cleaner signal. So that's all for the results that we got for the simulation code. Thank you.
Assalamu alaikum. I'm Umar Mantugu. So for my part, I was tasked to do the DFT manual calculation. So so for the DFT manual calculation, we are asked to calculate xn from 1 to 1 0, where the 1 is n equals to 0. So for the calculation, we use the equation xa from n equals to 0 to n minus 1, xn e exponential minus j 2 pi nk over n. So we got the n equals to 4, which is the length of the xn. So here we substitute for x0 we got 1 and we cancel, and here we added the x0, x1, x2, x3 uh, to get 4. So this is for x equals to 0. Same as the first one, we did the x equals to 1. Also substitute the k value and compute it. If you compute, you will get minus 2j. And the second one, which is the third one, which is k equals to 2. If you substitute the k, we cancel here, we substitute, and we'll get 0 here. And for the last one, it's k equals to 3. When you substitute the k value and the x0, x1, x2, and x3, so finally we'll get uh, 1 plus 2j minus 1 plus 0, which will get 2j. So overall, we'll get xk will be equals to 4 minus 2j, 0, and 2j, where 4 is the n equals to 0. Thank you. I'll pass to the next presenter.
Okay, my name is Nazimin Azila. So I will talk about conclusion. In conclusion, this project is directing attention towards implementing frequency domain noise filtering with the discrete Fourier transform and fast Fourier transform in three manners: manual, MATLAB simulation, and microcontroller Arduino to design, simulate, and optimize algorithms. The objective of this project was to analyze and filter noise signals in real-time embedded use scenarios in audio or ECG signal processing. This project showed remarkable results as the manual. MATLAB and Arduino microcontroller based FFT are equal and prove the possibility of frequency domain noise filtering in different platforms. The transition of those algorithms to microcontroller boards enables real-time operations and the possibility of connecting them to other sensors and actuators, which subsequently implements this solution in a real-life setting. Theoretical knowledge and practical experience has been gained throughout this group project, which can be applied further in future tasks to improve performance so it can accommodate different applications. Thank you.